Hi everyone, welcome to the Nuvoton Level 1 training. I'm Abby, Field Application Engineer of Nuvoton. Today, I'm going to introduce the PWM function of our NuMicro M031 and M032 series. In this section, we'll tell you what PWM is, what features and functions it has. We'll also go through the block diagram to let you know better about PWM. PWM stands for pulse width modulation. It is a way to control analog devices with a modulating digital output. Usually, we use digital way to control a GPIO pin, which is either on or off. However, if we don't want to control it just by on and off, we can use PWM to control the level of it. For example, when we are controlling an auto motor, on means run in fully speed, off means fully stop. If we use pure digital way to control the motor, it will have only two levels. There would be no other levels between. PWM provides a way to control devices by levels. PWM makes it by providing different level of energy in a unit of time. For example, when controlling the auto motor, if we give 100% of energy in a unit of time, it will run in 100% speed. If we give 60% of energy in a unit of time, it will run in 60% speed. Therefore, by PWM, we can control the levels of applications like auto motor speed or LED lighting. For PWM, period and duty are two important parameters. We have mentioned that PWM controls the level by providing different energy in a unit of time. Period means the unit of time. Duty means the proportion of on time to the period, which also means how much energy provided to the period. Therefore, by controlling period and duty, we can control analog devices by different levels. Take the graph on the right-hand side, for example. If we use the setting that the duty is 60% on to control an auto motor, it will run in 60% speed. We can also adjust it to run in 40% speed by setting the duty as 40%. The implementation of PWM is done by a counter and a comparator. There is a counter used to decide when it should be on duty. The counter value decreases from the value of period. A comparator value is used to tell when to switch from on to off. For example, if the period is 100 and the comparator is 40, the pin status will be switched from on to off when the counter reaches 40. Therefore, in a period, there will be 60% on and 40% off. The counter value will be reloaded to the value of period once it reaches 0. Means it will be reloaded to 100 in this case. Let's see an example of LED lighting. In this example, it is a little bit different from the auto motor case. Considering the hardware ability of LED light, usually we connect LED positive charge to an external power supply and connect LED negative charge to a PWM pin. Therefore, when PWM pin is on, it means to turn off the LED light. And when PWM pin is off, it means to turn on the LED light. By the example below, if we use PWM to control the red LED light by the period and duty on the right-hand side, the red LED light will be on when it's off duty. This is an example to show that you can use PWM in a different way according to the application. In our BSP, we provide an API for setting the period and duty of PWM easily. The API is PWM config output channel. The first parameter specifies the PWM module, and the second parameter specifies the channel number of PWM. The third parameter is the frequency to generate each modulating signal. It also means the period of PWM. The last parameter is the duty cycle by percentage. Take the function call in the bottom for example. It means to set the channel 0 of PWM module 0 to output waveform by 100 Hz and 50% duty. PWM's features are similar in all of Nuvoton microcontrollers. The features we are going to introduce here are specific for NuMicro M031 and M032 series. First, PWM supports maximum clock source frequency up to twice HCLK. It means that if the CPU can run up to 72 MHz, PWM can run to twice, which is 144 MHz. For each PWM module, we provide 3 counters for 6 output channels. Besides, the 6 channels could be configured to 3 complementary paired output channels. It supports 12-bit Prescaler, which means you can reduce the frequency by the divider ranged from 1 to 4096. The counter we used for PWM is a 16-bit counter. It can be operated as an up counter, a down counter, or an up-down counter. For PWM, it supports below-pin output functions. As we mentioned in the former page, the channels could be configured as either independent or complementary. Besides, the 3 counters it has can be configured to be synchronous. After PWM pulse is generated, we can modify it by mask function, break function, and polarity control before outputted. Mask function can fix the output to high or low no matter what pulse it has generated. Break function can fix the output to high or low when got an external signal or an internal error signal. Polarity control is used to make the output phase opposite. Like the LED control we mentioned before, we can use polarity control to make 60% duty high into 60% duty low to let LED on at 60% brightness. At last, the enable function is used to control whether the pulse will be output to the I/O pin. Besides, in complementary mode, we also support dead time insertion. For some application, like motor, it can be used to delay the time transferring from low to high. It is used to avoid 2 paired channels to transfer status at the same time. You can use these pin output functions according to your application. PWM also supports capture function while PDMA. The data would be stored in SRAM without CPU intervention. Besides PWM, we also support BPWM, which is basic PWM. Most of the features of BPWM are the same as PWM. The difference is that BPWM only provides 1 counter for 6 output channels. Unlike PWM, it doesn't support complementary channels. Like PWM, BPWM supports below-pin output functions, independent channel configuration, mask function, and polarity control. It also supports capture function while PDMA. Let's go back to PWM. Here is the block diagram of PWM. There are 3 counters in PWM. For the independent mode, 1 counter is mapped to 2 output channels. The 2 channels will both use the same counter for counting. The comparator of each channel could be set individually. However, for the complementary mode, 1 counter is mapped to a paired complementary output channels. Both comparators will be used for the paired complementary channels. For example, for paired complementary channels, channel 0 and channel 1, comparator 0 and comparator 1 are used. By setting comparator 0 and comparator 1, it could have multiple event points and generate various poles. In basic PWM, it only has independent mode. It only has one counter, therefore all channels use the same counter. After block diagrams, we would like to talk about the clock source of PWM. In order to have higher output frequency and better duty resolution, we support maximum clock source frequency up to twice HCLK. For example, if we set the clock source of HCLK as half of PLL volt, it would be like set the clock source of PWM as PLL volt. Here is the example of how to set the clock source of PWM. In the code, it first sets the clock source of PLL as 96 MHz, and then the clock source of HCLK is set to half of PLL. Afterwards, it enables the clock of PWM Module 0 and set the clock source of PWM Module 0 as PLL. Therefore, the clock source of PWM Module 0 is twice HCLK in this case. After the settings, the clock of PWM will start to work. We have mentioned that there are three counter types that PWM counter can use. They are up counter type, down counter type, and up-down counter type. For up counter type, it will count up from 0 to the value of the period. When it reaches the value of the period, it will be reloaded to 0 and start over. For down counter type, it will count down from the value of the period to 0. When it reaches 0, it will be reloaded to the value of the period and start over. For up-down counter type, it will first count up from 0 to the value of the period. When it reaches the value of the period, it will continue to count down to 0 and repeat. You can choose either counter type in your PWM application. We can generate PWM modulating signals by setting an action when a specific event happens. Therefore, there is a mapping between events and actions that we have to set for generating a PWM pulse. The events could be when 0 point is reached, when period or center point is reached, or when counter equals comparator. The corresponding actions could be X, means do nothing. L means output low signal. H means output high signal. T means to toggle the signal. Take the first graph on the right-hand side as example. It defines 6 event action pairs. The first is 0 equals L, means when the counter reaches 0, like 0.1 in the graph, it would output low. The second is CMPU N equals X, means when the counter counts up and reaches the compare value N, like 0.2 in the graph. The action would be do nothing, therefore it stays at low. The third is CMPU M equals H, means when the counter counts up and reaches the compare value M, like 0.3 in the graph, it would output high. The fourth is center equals X, means when the counter reaches the center, like 0.4 in the graph, no action needs to be done, it will remain high. The fifth is CMPD M equals X, means when the counter counts down and reaches the compare value M, like 0.5 in the graph, no action as well, remain high. The last is CMPD N equals L, means when the counter counts down and reaches the compare value N, like 0.6 in the graph, it would output low. Therefore, by the settings between events and actions, we would get a PWM pulse. Another way to generate pulse is by setting CMPU, CMPD, and 0. CMPU means the counter is equal to the comparator when counting up. CMPU equals L means that when the counter is equal to the comparator when counting up, the output should be low. CMPD means the counter is equal to the comparator when counting down. CMPD equals H means that when the counter is equal to the comparator when counting down, the output should be high. 0 means when the counter is reloaded to 0. 0 equals H means when the counter is reloaded to 0, the output should be high. The graph on the left-hand side shows an up counter type. It defines CMPU equals L and 0 equals H. Take compare data equals 0 as example. Since the comparator is 0, it will be low all the time, which is 0% duty. Take compare data equals 1 as example. Since the comparator is 1, it will be high before 1 and low after 1, which is 20% duty. The graph on the right-hand side shows an up-down counter type. There is DIRF to show the direction of counting. DIRF equals 1 means counting up. DIRF equals 0 means counting down. In this graph, it defines CMPU equals L and CMPD equals H. Take compare data equals 0 as example. Since the comparator is 0, it will be low all the time, which is 0% duty. Take compare data equals 1 as example. Since the comparator is 1, it will be low after 1 when counting up, and it will be high after 1 when counting down, which is 25% duty. Therefore, we could generate different PWM pulses by different ways and settings. The API used to set Prescaler value is PWM Set Prescaler. By this API, we could set the Prescaler value of a specific channel. The example shows to set the Prescaler value of channel 0 of PWM module 0 as PWM Prescaler. Notice that we use PWM Prescaler -1 here. It is because that we will use the third parameter plus 1 as the value of the prescaler in the API. It is used to avoid dividing by 0 problem. Therefore, if you want to set the prescaler as, for example, 10, the third parameter should be 10 minus 1 equals 9. The API we use to set the value of period is PWM Set CNR. By this API, we could specify the period of a specific PWM channel. The example below shows to set period of channel 0 of PWM module 0. We also need to set a compare value of PWM. This API, PWM Set CMR, is used for it. By the example below, we can set the comparator of channel 0 of PWM module 0. We've talked about how to generate pulse before. One of the methods is to specify the action for each point. We also have an API for this pulse generation. There are 4 points defined in this API. They are 0 point, compare up point, period or center point, and compare down point. Actions can be used are defined as do nothing, output low, output high, and toggle. Therefore, we can specify action for each point and generate a pulse we want by this API. After all the settings of a PWM channel has done, there is one more API to call to enable the channel to output the pulse generation. The API is PWM Enable Input. After calling this API for a PWM channel, the channel will start to generate and output the pulse by its setting. Besides, don't forget to start the counter for PWM. This API, PWM Start, will start a PWM counter for a specific channel of a PWM module. Since every two channels share the same counter, start a counter means to start a counter for two channels. By the example below, it starts the counter of channel 0 and channel 1 of PWM module 0. At some points, PWM can trigger interrupt. When interrupt is enabled, NVIC Enable IRQ function should be called to identify the handler function of the interrupt. In this example, period interrupt of PWM module 0, channel 0 is enabled. NVIC Enable IRQ function defines the handler function as PWM 0 IRQ handler function. Therefore, when the period interrupt is triggered, it will be handled by PWM 0 IRQ handler function. User can define what actions to do for each interrupt in the handler function. On the right-hand side, we list 3 API that could be used to enable PWM interrupt. PWM Enable Period Interrupt function is used to enable period interrupt of selected channel. Notice that the third parameter is not used. PWM Enable Zero Interrupt function is used to enable zero interrupt of selected channel. PWM Enable Duty Interrupt function is used to enable duty interrupt of selected channel. Duty interrupt type could be either PWM Duty Interrupt Down Count Match Comparator, which means interrupt will be triggered when comparator is matched during counting down, or PWM Duty Interrupt Up Count Match Comparator, which means interrupt will be triggered when comparator is matched during counting up. Above is the introduction of PWM. Thanks for watching. You could subscribe our channel for more information. Besides, please do not hesitate to contact us if you have any questions.